Hello, everyone, and welcome to our Friday seminars. It is my pleasure to introduce to you our speaker today, Dr. Ramses Mena from UNM in Mexico. Ramses is a professor there at the Department of Probability and Statistics, and he is also the director of the Research Institute for Applied Mathematics and Systems at UNM. He received his PhD in mathematics from the University of Bath in the UK, and he also did his undergraduate and masters from UNM itself, undergraduate in actuarial science and masters in statistics. So he is quite interdisciplinary in that sense. And he has a very distinguished and illustrious profile with a long list of publications, firstly, and many other awards and distinctions. So I'm not even going to try to count all of them. All of them, that will probably take a whole seminar. But here are a few highlights. First of all, he has a very extensive research profile with over 60 publications, all in well-reputed journals, supervised a lot of students in various levels, and he's also been instrumental in fostering various collaborative opportunities and initiatives at UNM. And his research is well-funded through multiple grants, and he has received various awards and distinctions, both international and national, for his work. He was also the president of the Mexican Statistical Association, and he is an elected fellow of the ISPA, where he also founded the Region Non-Parametric section. Right. And these are just a few of his many distinctions, both in research and service. His main research interests are in Bayesian non-parametric, applied stochastic processes, time series analysis, and simulation-based problems and their applications. And today he's going to tell us about some of his recent interesting work on exchangeable random measures and stick breaking priors. So please join me in welcoming Ramses.
Thank you very much, Abhishek. Thank you very much, everyone. Thank you, Sharmista, for inviting me and the whole group. I'm very happy to see some people here that I haven't seen for a while, and some new people as well. It's always a pleasure, of course, to come. This is my first time in this part of Texas, although I knew about the existence of the place for many years, but never actually had the opportunity. So it's a nice occasion. So, but I was impressed you didn't read any of the things you said. I was really impressed. I'll take note on that. So I'll speak about this work, which is a work in one of the areas I work on. I'm based in parametrics, and it's part of the thesis of Maria Fernanda Gil Leiva, a PhD student, a very bright PhD student, that later on became in some other papers. One with Theodoro Nicolaris, a colleague from Athens University in Greece, and Antonio Lioi and Igor Prunser from Bocconi University, who are all colleagues of mine. And we are developing a new paper that hasn't been published, but the idea is to speak a bit of that paper as well. So the idea is very simple, and let me see how this works. Okay, not working. The other way around. Sorry. So these are the plan of the talk. Essentially, I will firstly introduce a bit of stick breaking processes. Previous to that, I tried to convince them about Bayesian parametrics, although I think there are many Bayesians here. There might be a couple of those who are not really Bayesian, so I've tried to convince them a bit of that. Then I'll speak a bit of exchangeable stick breaking prior, the idea that is written in that thesis, and some of the extensions. So essentially, the way I like to teach statistics when I do a lecture is to start with the idea of random. Oops, I'm going down. Sorry. With the idea of a random phenomena that we, in probability, if we try to do statistical induction, doing probability theory, we try to encode to random variables that model or capture the phenomena that we're interested in. All right. So statistical learning always comes to the study of the stochastic dependence between that. And that's very a simple concept for Bayesian statistics. Essentially, you have a random a sequence of random variables. You require that infinite set of sequence of random variables in order to be able to do that projection in the past and the future, and to have the coherence to do predictions and to speak about statistics. Otherwise, it's difficult if you don't do that infinite here. So logical independence or physical independence of a phenomena not always implies that you have stochastic independence. Actually, if you want to learn from a process, you want to learn from a process of doing some sampling, you have to have stochastic dependence, even though the actual phenomena that you're probably modeling is physically independent. That's a nice way to put it. I can go on in examples that you have physical independence and then you have stochastic dependence, do a Google search and whatever words you might imagine, and then you are in that position, right? So essentially, under physical independence, all you can assume about the observations under physical independence is that you have certain symmetry, certain stochastic symmetry, all right? That stochastic symmetry will allow you to do a lot of things, will allow you to predict future moving in time if you want, with that assumption of physical independence. If you put other things that stochastic process time, then things change, but let's stick to that. So exchangeability comes naturally to this concept. So you have invariance of the way you observe, stochastic invariance, meaning that the distribution of something I'm modeling in this room, it doesn't matter how I sample these random variables. There is a stochastic dependence behind that, even though the machinery at the bottom is physically independent. And we will understand that in a bit. Okay, so exchangeability is an old concept for probably many of you that you study in probability, and it's a stochastic symmetry such as stationarity or reversibility, other stochastic symmetries that are studied for a lot of things in probability theory, but also in statistics. There is a nice analogy. There is a theorem that tells us that you have this symmetry, then you can decompose by thinking of that phenomena. I'll try to go back here. But thinking of that joint distribution of the phenomena I'm trying to model, or the sample I'm trying to capture with this stochastic phenomena as conditionally independent given something. So if you take this integral off and this delta measure, I'll discuss that later, then you have independence. So given something, you have that. So there's a famous theory by De Finetti that tells us that you can decompose through exchangeability through conditional independent identically distributed random variables, a phenomenon. So that's the idea that goes behind that. And then this probably is a bit fast, but the exchangeable sequence then is modulated by the law of that thing that we are not aware of. It is the limit of the things that we are looking for. This distribution that is called sometimes the Finetti distribution. So let me go a bit ahead and then I'll come back because otherwise you're not going to understand things. So the Finetti, what it does is this decomposition here. So given something, oops, I went down. So given the limit of the things I don't know, and that limit is random, then you have this decomposition. So probably I'm not doing it I'm messing around with this. So essentially, exchangeability is a way to say, look, you have this symmetry. So the Finetti wonders, what can I say about this sequence if I only start from the fact that you have this symmetry? So what I can say is that can be decomposed as a conditional independent given something, and that something is random, and that random is the limit of the things I don't know about the phenomena. So in that case, it's very simple, and exchangeability includes many cases. For instance, that measure, if we take the space of all probability distributions as a particular set, let's say the set that you like to model things, whatever Polish space. So if you take that space of distributions on there, and you degenerate this is just a random distribution. Could be the normal distribution 0, 1, for instance, right? Or the normal distribution with mean theta, for instance. It's just one distribution. So you degenerate this measure in that, and then you have independence in that particular case. So independence, as we know it in stochastic independence, is a particular case of exchangeability. And that's an important thing to keep in mind. It's a natural thing, but it's also very important to realize that if you degenerate that measure in a particular distribution, you have independence as a particular case. So you can also have a parametric family. If you degenerate this the Finetti measure, sometimes called this Q measure, in a particular, say that the space of all unimodal distributions, or the space of all normal Gaussian distributions, right? So then you have in that huge space of all probability distributions on the space I'm trying to work on, a particular way to measure that. And that has a nice interpretation in Bayesian statistics, because then it means that the random uncertainty of a phenomena that I'm studying, there are two kinds of uncertainty. There is this view from Michael Goldstein that says you have two sources of uncertainty. The one you can capture with the arrival of new information, and the one that is just the nature of the phenomena that you cannot model. So that in Bayesian statistics falls very nicely, because essentially the bit that you cannot model is the model you assume, right? Say the normal, the gamma, whatever distribution you're assuming. So what you don't know are the parameters, and you want to learn about the phenomena, you learn about the parameters with the incoming of new information. So in this parametric setting, it falls very nicely, because it says, look, you have a parametric family here, like the normal, for instance. You cannot learn, you know that your phenomena has a univariate, symmetric, very nice way of doing it. You're assuming that is normal, right? Then you can only learn about the parameters, the mean and the variance, for instance, right? And then that is what is called sometimes the epistemic uncertainty, and this is what is sometimes called, referred as the random uncertainty of the phenomena. So this is a view. It's not the only view of Bayesian statistics, but it's a nice philosophical view and very fast way to say Bayesian statistics exchangeability allows you to do this, right? Let me move on here. So what is Bayesian parametrics then? So I try to model infinite dimensional sets of this space of probability measures. So essentially, I want to put mass in elements, random elements, that can capture whichever distribution you have in the space of all these distributions. So essentially, you have a sort of consistency here. We have a lot of experts on this area here in this school of statistics. Essentially, you say that any distribution within a distance of epsilon, that epsilon can be anything, can be captured by this Q. So you are dense in a sense. Of course, dense in a sense that whatever the phenomena you are modeling, you are not going to say it's normal, you're not going to say student T, you're not going to say by my model. No, it's any distribution can receive, or to certain topology, that D, that you are modeling this. So essentially, if we think about it, it's just like tossing a coin. Like before you toss a coin, a Bernoulli coin, you have a number between 0 and 1, right? So you toss a coin with this law, and you get a distribution, a probability distribution. And that distribution might live in the whole space. It's dense in the whole space of distribution. So that's based on parametrics in a fast way. If you do that, then you end up with this expression, which is the general expression of definity, which tells you that you don't know the mean, the variance, or other characteristics. You don't know anything. So you don't know the whole form of the distribution. So you don't know, the ignorance goes to the distribution itself. So this is when you have to model the distribution, that becomes random. So this is the random probability measure, and this is the law or the distribution of that random probability measure. So in a way, it's the same idea that we have in probability, but instead of just having a random variable that we model with a particular density, we have a function, and a function is an infinite element. And as an infinite object, it has peculiarities with mathematics, how to model this, right? So, but that's the idea. The idea is to model that infinite distribution and try to place a probability measure on that infinite distribution. If we are able to do that, which we always do with Gaussian processes, which other ways to measure curves and functions, infinite dimensional objects, right? We do that all the time. So essentially, what I like of statistics is, of Bayesian parametrics, is in one stroke, as I would like to say it, is you model both the model, the form, and also the parameters. So you model both uncertainties, the random uncertainty and the epistemic uncertainty. Of course, it's not like as simple as you would imagine. It's again a model. And again, as a model, you have to model this Q, and that has its complications. So Bayesian parametrics is about thinking about this Q, for instance, the set of all discrete distributions, all of them. That would include, for instance, if you are in the integers, the Poisson, the negative binomial, whatever, right? So if you use this notation here with the D, discrete or continuous, those are infinite sets that we want to sort of randomize, a sort of study distributions there. So all taken there, right? It's more or less the idea. So I start from the random phenomena, justify it, that the way to deal with the random phenomena in order of statistics is use exchangeability in this line of thinking, and then do that through the study of a random probability measure, that Q. And then the idea is simple. Now we need to do what we do in statistics and the probability. We need to construct random probability measures, right? We need to construct the normal, the gamma, whatever, right? The distributions that we are going to use for this. So it's just a distribution with a different support, and support is a bit bigger, right? But the idea is the same. It's just the same. So questions here? It's a good moment to shout before I carry on. No? Val is just looking at me, but not saying anything. Okay. So I carry on. So that's the idea, right? Let me see if I'm not missing anything. One stroke model both, but we still need to model that Q, that distribution. So Bayesian parametrics is about constructing the first step. Ferguson, 1973, was to create a way to model these things. So there are many ways that people that are already thinking is very quick to model these things. How can I model an infinite object? Well, one way, natural object, is think of a stochastic process that has a particular trajectory and do something with this trajectory to transform it into a density or to a CDF or into a survival function to something, right? So that's a nice way to do it. That's the way, one of the ways Ferguson did it. And there is a nice theory behind this that also borrows a lot of the theory of stochastic processes. And that's a bit of what I want to talk in the next one. So there is a huge story on that idea. If you look at this point, and I know you're looking at the slides, but think about this. Think of a Poisson process, right? The Poisson process pretty much looks like a CDF, right? So something like a Poisson process with a bit more intensity of jumps. If you normalize it, then it behaves like a CDF. So what is a Poisson process? A Poisson process is an infinite independent increment processes, right? So that property of it in the independent increment process means that the increments, the jumps, are independent. So that property, when you pass on from the reals to any Polish set, is known as the completely randomness. It was introduced by Kidman. It's the same idea. So the idea of those processes, think of this M at the top at the moment for this stochastic process, the Poisson process, if you want. And the idea of that is that we want to use the law. We want to know the law. We want to know that Q. So we know the law of the process. We can do many things. So we know the law of independent increment processes through the Laplace transform. We know how to say something about it. And that has been used a lot. Of the theory was used indirectly, not in that generality, by Ferguson itself. And then later on in one of the theses by Igor Prunzer and some of the papers by Rogazzini and James et al., they set up the theory to do this construction. So essentially the idea is this one. Think of that random measure, that completely random measure, satisfying this condition. This condition has to be satisfied so I can normalize and no funny business happen, right? Okay, so this is a measure, think of a process, and you normalize it, so integrates one. It's still a measure, right? And that's it. You cannot divide by zero, so you cannot have a Poisson process, you have to have an infinite process, an infinite activity process, so sort of like a gamma process, right? So essentially that's the case. This world is what has been ruled in the Bayesian parametric world. They are doing a lot of the things with these kind of models, the Dirichlet process, many of the processes, the gamma process, the stable processes, many of the processes that are used as law of random probability measures fall into this class because they have that tractability, the tractability through the Laplace functional. And then things are easier with that. But when you normalize, you lose the independent increment properties. Okay? So this P, whereas this mu has independent increments or completely randomness, when you normalize it, you lose that. But then you have a different sort of story that is called exchangeable increments. So essentially, you have something that conditioning on that, you have independent increments, right? It's the same idea. So what I'm going to talk about in this talk is that whereas the models here in this circle here, the normalized completely random measures, have ruled out most of the applications, there are many models outside this that are interesting from the Bayesian parametric viewpoint and can be also used for inference. That's pretty much what I'm going to say. So the Dirichlet process lives here as a particular case when the intensity measure of this completely random measure is the gamma increments. So what is this? This if you look at the S, only the jumps, is the component of the Levy intensity of a gamma random variable. So if I take a gamma random variable, compute the Laplace transform, and what is in the exponential of that Laplace transform, see what is on the jumps, that's that bit. So it's a gamma random variable. So the increments there are gamma, right, in a way. So if you have that, I have infinitely many jumps in zero epsilon, in a particular set that is not necessarily infinite. So that means that you have infinite activity. With that, when I can normalize without any problems. Anyway, this is the story of Dirichlet processes, but we are not going to go to, we are going to do it much simpler than that. But you'll see how. So the whole world of exchangeable random probability measures, which is a nice work done by many authors in the past, they have also a representation. The same representation you have for the Laplace transform, you have the same representation for exchangeable random probability measures. So we wonder at some point, what is the class of exchangeable random probability measures? Why is this class so confusing, right? So theoretical. So it happens that that is the same class of species sampling processes that we'll explain later, and stick breaking priors. And the stick breaking priors is already proven. It's like something we identify if we have read papers in Bayesian parametrics, which is simpler. So the whole class of exchangeable random probability measures can be represented as is the same class as stick breaking priors. So what are stick breaking priors? Is essentially think of this as a random density. Well, this is a random density with random weights and random locations. So just a pause here. So you think about any discrete distribution, like the Poisson, right? Then you have these values here, taking the values of the Poisson. 1, 2, 3, 4, 5, 6, 0, right? So, and the W are the weights of the Poisson. So any discrete distribution can be represented by some weights and their locations where the jumps happen, right? So if you randomize the weights and the location, then you have a random probability measure. So as simple as that. And then you forget everything I said before, because this is much faster, right? Okay. But how to construct weights that add up to 1? So there is a nice theory how to construct weights add up to 1, and that's what we want to see later. So in this notation here, the weights and the locations will be independent. Will be infinite sequence of independent random variables. The weights add up to 1, and these are IID with a particular distribution that we are going to call P naught. If you take the expectation of this P, very simply, since these add up to 1 and are independent, you have that the expectation of this P is P naught, right? So that P naught is our parameter. But now our parameter is a function. It's a function of infinite nature. So because we have an infinite distribution. So okay. So in a way, that's what's going on. So that normalized complete random measure, this space here, and I know those who already know a bit of Bayesian parametrics are wondering of why this moon shape is not part of this story, because when the locations and the weights are dependent, then you have non-homogeneous random measures. That means that when you jump, it depends where you are in time in that jump. And that is a whole story, completely different, and it doesn't fall into this class. But what we're going to be studying then, today's talk, is a subclass of these exchangeable random probability measures. And that subclass is the class where these are the stick breaking construction. So if you take the weights composed by these random variables, B, that we call length variables, or some people call them sticks. Some people call them, I call them length variables. Right? So these length variables, what tells you is you have a stick of size 1, and then you take a random variable, B1, and then this is your first length, and then you subsequently cut like that. All right, everyone like that. So if you do that, it's very simple, as long as you assume some basic conditions on the law of these random variables to ensure that they add up to 1. So constructing weights that add up to 1 is very simple through this story. So you can forget about the whole stochastic process theory, because that's all you need, all right? And you know that there is a theoretical background that ensures that you are in the class of these exchangeable random probability measures. So this is well explained, of course, in the paper that we'll refer later by Maria Fernanda. So most of the models that are in the literature, like the Dirichlet process or Poisson-Dirichlet process, they have independence in these random variables. So we are going to relax that. And why is we want to do that? Because we want to fall into some other models that are more interesting in some way. And we're going to see why. It's not just for fun, mathematical fun. There are some reasons for it. So stick-breaking weights, stick-breaking priors, or however you want to call them, these probability measures where you have the weights in this form, and as we said before, these are independent of the weights, and IIID from P naught. If you have full support, if this condition is satisfied. So it's very easy to check that condition. And it depends, this is going to simplify if these length variables are independent or are something else, right? It might simplify or not. It depends, this probability might be different. So, and the weights add up to 1 if you have this condition, essentially this moment condition, which again, this might be easy. For instance, if they are independent, this is it's very easy to compute, right? But they're dependent, you have to compute the whole of the dependency. So the idea is very simple. You think it's super easy, the idea, right? Okay, so that's the whole idea. And there are many things to justify this. The Disley process is a result when you have these length variables being beta independent, identically distributed with this variable. The two-parameter Poisson-Disley process, which is other of the models with more justification to be used in Bayesian parametrics, is when the length variables are independent but not identically distributed. That means you have a dependence, right? It depends on the length. And there are other models, and in the other models, there are representations. For instance, in the sigma stable Poisson-Kingman dependent, the dependence in the, sorry, I didn't say something. These are representations, all of them are representations. That means that one of these processes might have different representations. They're not unique, okay? So there is a representation for other kind of process, like for instance, homogeneous normalized, homogeneous completely random measures, normalized completely random measures. So in that moon, sorry, if I go here, go back here, Sorry. No, I'm going back. This thing is really the other way around. So if I think of this intersection here, this class of this intersection has also a representation already proved in a paper where when the length variables are dependent. And the dependence, let me see if I do it right there. And the dependence is that is here, right? It's this one here, right? So you have a particular distribution where all the dependence is there. So there are models out there that have been generalized in the Disley process that have a representation, a stick-breaking representation where the length variables are dependent. So the question is, why don't start with a full theory that models dependence and see what happens, right? So that's what we did in that PhD thesis with Maria Fernanda, all right? So essentially, there are too many problems that are studied in Bayesian parametrics historically. There are many, but there are two main problems. One is the clustering, and one is the density estimation. The clustering is studied because you have a discrete random probability measures. So since they are discrete, might be tides. So once you select a random probability measure that is almost surely discrete, that Q puts mass puts mass 1 in the discrete, then you have ties, and the ties create clusterings, create ways to measure partitions. So that's the idea behind no parametrics. So once you select or pick a no parametric process, based on a parametric prior, you are inducing at the same time a distribution of the clusterings, and therefore able to do inference on that because you are putting a prior, you are putting a posterior, right? So in that computation is done very easily through this expression here, very easily mathematically, but not very easy to compute, right? So and similar inference can be done for those more into the story of mixture models in the past century. With what is called the allocation variables, meaning these allocation variables, if you have a bunch of data, tells you where is the group that the data comes from. So essentially, D1 equals to D1 small one here, it comes from that group. So essentially, each of you has a label that tells you which group you belongs, and that's modeled through this D variable, all right? So that's the idea. So there are two ways to do it. One is with the space of partitions. I'm not going to go into detail here, but if you like mathematics, if you like combinatorics, the space of partitions is very fun business to do. It's a huge space. It's a space that is not ordered. It's a space that is not ordered, and it's a mess to optimize this space. And there are many papers on that because it's not ordered. I mean, if I ask here, 10 people here, how many? Well, there are more than 10 here. There are many, like 50, I don't know. And I see how many groups can we form with 50 people, I wouldn't be able to say the number. It's just huge, it's massive. the number of groups that I can do with you here, right? The different grouping system. So we are putting a prior on that, with that, right? So I think for 10 people, it's like 115,000. Is the Bell number, right? It's well known as the Bell number. So essentially, you can do that with these two distributions. This distribution is the one that people like the most, and these expressions are called a PPF, exchangeable probability partition function, right? So essentially, they allow you to measure these things, but I prefer this one in many senses, because this one, unlike this one, can be ordered in a different sort of way. So it depends what you're doing. Sometimes this is better than this one or the other one, all right? But both can be used. And I'm justifying this one because this one, as you might predict, can be computed with the whole story, whereas this one only with those normalized completely random measures. So there are two examples of that. The Dirichlet process, as we saw, that is here. Essentially, the Dirichlet process has these weights. If you see the weights of the Dirichlet process, you have the means of those weights are geometric, because, and these are order, right? The means of those, but they are not ordered in a almost surely way. If you do the decreasing, the random probability measures where the weights are, all the weights or the length variables are equal to one variable that takes value between 0 and 1. That's simple. So you have a way to create a random probability measure where the weights, instead of being stick breaking, well, they are still breaking, they are just lambda, 1 minus lambda to the power of I minus 1. And that very simple model is dense again. It's dense in the sense that you can replicate any distribution, any discrete distribution with that. As simple as that, all right? As long as this random variable is random. You cannot fix a number. It has to be random. So these weights are the geometric weights. It's a paper Stephen Walker, Ruth Fuentes Garcia, and I introduced it back in 2010, I think, although it's a paper in 2009 as well that uses them. So the idea is the simple model looks much simpler than this one, because here I have an infinite number of random variables, whereas here I just have one, right? It would be very nice if that model would be everything that we need, because we have a model that is dense, but it's not as complicated as the other one. And people wonder, people always ask me, what is that? I don't understand this. Think of the normal distribution. The normal distribution is dense on the real, right? You can place mass. But also the student T distribution or the Cauchy distribution is dense, and it has a different probability in the tails. It's the same here. You have two dense distributions with different probabilities in different sets, right? It's the same idea in a different dimension. So they both have full support, but they both are exchangeable. I mean, in both cases, you have the length variables are exchangeable. So that justifies the idea of a little bit that one is full dependent because they are all the same, and one is full independent. So what is in between is very interesting. And I say why, because this process, for instance, this geometric process has been proven to be very good for density estimation. If you know, you go back to the story in mixture models in the 2000s, there was a lot of jumping in and out, because they have this label switching problem that causes a lot of problems when you're estimating the parameter, the mixture, right? And that happens essentially because the weights are not ordered. You don't have constraints in the weights. So you change that a lot in the orders. So if you put a constraint that the weights are ordered, like in the geometric, you have this kind of example, and I explain. This example here is the dynamics of a mixture of Dirichlet process when you're mixing the densities. And these are the 100 iterations after 10,000 of convergence. So essentially, you still have some wiggling here going on. You are not deciding which is the best value because you are jumping in your MCMC process, right? Whereas in this one here, for instance, oops, no. In this one here, I have the first 100 iterations, not the 100 iterations after 10,000, the first 100 iterations of the geometric. And then you see how they adapt very quickly. And that's because the weights tell you a priori, all of this is a priori. To which are you going to give, to which element of the, which label are you going to give the more weight, right? And that actually works a lot, and we have been proving that in many papers, that for density estimation is much better than the Dirichlet, for density estimation, but not for clustering. And the idea is not for clustering because it changed completely the story. I'll explain that a bit later. So essentially, the whole idea is exchangeable stick breaking processes is the same idea as we had before, but where the B's, the length variable, are exchangeable. It's themselves. So now it might be a bit of a loop because we're starting from a exchangeable setting to do statistics, and then we say the random probability measure, we're going to model it to something, right? And that something is a stick breaking prior where the length variables can be exchangeable themselves. Yeah, jump.
Okay, question about the previous slide.
Hold on. Let me go back.
The difference that you see is that only difference because of the sampler, which how the sampler behaves, or there is how a frequency computable figures exactly still.
Oh, that's a very good question. Actually, we did it. We did the examples. We did the example for exactly for a small data set. For 10 data set that we have 115 in order to be able to reply to that same question because we have the same doubt. So essentially, we did the posterior distribution exactly. We didn't do any MCMCC and compute the both two things. So that's presented in a paper in 2010 with Stephen Walker and Ruth Fuentes as well. And we compare it, and the same expression happens. I mean, what's going on is that you are digging between the weights, and then you have. I didn't discuss that, but you have a. I don't have something to write. Oh, you have one. Thank you. So essentially you have a. This is your measure, right? So this is equal in distribution. For any permutation row. So essentially, that what it's saying is that when you do inference on that, you have no identifiability on the weight that is attached to that label. So when you impose the fact that you have different weights and they're all decreasing, that diminishes. And in the infinitum, that identifiability is corrected. Because there are other kinds of identifiability related with mixture models. That's why I always say that, right? But that's the point, right? Essentially, that's the idea, and that's the good thing about the geometric. At the beginning, some people say, no, it's not full support. We prove it has full support, and it has been proven it has full support, right? So, of course, it's not as good as you would like for some applications. Again, you go back to the normal or the generalized hyperbolic. The generalized hyperbolic is the distribution that has full support in the reals, but it can be biased or can have peaks or whatever, whereas the normal is very nice, right? But they both are full support, right? So the idea is to capture this in a single model, both the digit and this one. And as I was saying, both of them are exchangeable. And then what we did in that work is start with the exchangeable setting. So we start from the bare assumption that the length variables are exchangeable. So you do that, I go quickly, the whole thing can be replicated, right? So essentially, you have a very nice condition on the Levy measure of this exchangeable sequence. And that condition allows you to have this theorem that essentially tells you that you have full support and the weights add up to 1. And the condition, which is in the random probability measures, then translates into the prior guess at the shape or the expectation of that nu. Let me see, this nu 0, right? Translates into that. So if you have that the random probability measure has this condition, the weights add up to 1, but that translates into that when you have this. So that means that if the sticks, the random variable, like the beta, you're going to choose for the sticks, has this property, which pretty much is very simple to achieve, then you have that the weights add up to 1, right? So the nice thing about this is that you have the limit. So when you start with this process, which is the generalization, now think of it's not the Dirichlet process, it's not geometric, it's something in between, essentially by assuming that the stick breaking length variables are exchangeable, right? So if you have that, then the random probability measure converges to the Dirichlet processes or to the geometric, depending of the random probability measures goes to it degenerates into a beta random variable or into a particular random variable, right? So you recover both models with a single model, all right? If this is a species sampling process, a proper species sampling process that which weights add up to 1, then the controlling of the dependence is going to be done by the probability, meaning that you have a sequence of exchangeable sequence of length variables, since they are discrete, modeled through discrete random probability measures, which is the probability that they have a tie, any two of those. So they get exchangeable, pick any of two. You can change, I pick here 1 and 2, and this probability will control, this probability is between 0 and 1, and will control whether you converge to the digit or you converge to the geometric, all right? So, and that's it. That's a very simple story, right? It's a very simple story because, for instance, if you take this random variable, this theory can be recovered. I mean, I'm taking here, I'm being very, trying to compare everything with the geometric and the digit, but there are other models, right? So if you take this random variable to be the beta, then this is the Dirichlet process, the random probability measure that modulates the length variables. And then the type probability is simply this proportion here that you remember is the weight attached to each point in the empirical measure of the predictive of the Dirichlet process, if some of you are aware of it. So other thing we discover is very nicely is precisely what I was explaining before, the ordering of the weights. So if you move on the weights, if you degenerate that into a beta or into a random variable as we did before, then you have size bias weights, as you do with the Dirichlet process, or you have decreasing weights as you do with the geometric process. And that changes the stories, because when you have size bias weights, you can compute the ePPF in a nice way. So you can compute that probability on the space of partitions. And when you have the decreasing weights, it's a bit more difficult. You cannot compute it very nicely. It exists, but you cannot compute it, right? And you can compute only the probability on the allocation variables. So what I'm saying is that if I have two of these options, the probability and the allocations variables, you can always compute it for both models, so we can do clustering with that. And that's what we do. So these are just the processes, the idea of the processes. You can see how this ordering that I was explaining here, how this ordering happens, right? Let me see, go back here. So essentially you have here this type probability with different values. And you see how the type probability degenerates into a single variable that tends, in the generated case, tends to be the geometric, and the other ones, this randomness in the weights that causes then the label switching and causes a sort of tampering down, right? So in a way, this is telling you, if you're going to apply the model, and that goes for any mixture model, if you're going to apply a model and you are able to control this ordering of the weights, then you are able to control how much are you going to get this label switching and how much you are not going to get this label switching. We haven't used it for that purpose, but that's a good idea, actually. And so this is just the behavior of this Kn. This Kn essentially is sorry, this probably was presentation more focused people in Bayesian parametrics. The Kn is the number of distinct groups in that probability, in that space of partitions I was saying. So essentially you have a size, let me try to explain it very quickly, probably here. So you have a set of size n, and since there are ties, you can encode this set into a set where this Kn is less or equal than n. So essentially into a unique value set. And this Kn tells you the unique values, the number of unique different groups. So that Kn has a lot of properties and characterizes random probability measures in many ways, also in Bayesian parametrics. So what we're doing there is trying to sort of explain what happens with that. And it has, for those people that like Arnivan or the people that work a lot, they has a lot of properties as well, right? So we devise now, is not in this paper, but we devise now a way to compute it exactly in sort of a different way. So the story goes Then you have exchangeable length variables. You can have Markov stick breaking processes where the exchangeable, when the length variables instead of being exchangeable are Markov, right? And I explained something that people might be thinking here. Oh, but there was a story about dependent Dirichlet process. Yes, but that was to model things that are dependent in time. Here we are modeling again the random probability measure static, where the dependence in the length variables can be anything. Well, barely anything. So the Markov stick breaking process, the story goes, is pretty much the same. But with one thing that we like a lot is that we cannot recover with the exchangeable case the two-parameter Poisson Dirichlet. So we wanted to have the same we had with the Dirichlet and the geometric. We wanted to have the two-parameter Poisson Dirichlet process and other processes here. So in order to have a better model to be able to compare, and with that we can do that with Markov. We cannot do that with exchangeability. So of course there are many nice ways to do it. When you have exchangeability, you have this, a measure controlling the dependence on all of them. When you have Markovianity, you have a clear dependence. You know, the past and future are independent given the present. And then you have this line of dependence. And everything is determined in the stationary case through the transition probability that we denote with this nu here. So the convergence that we're going to have now in order to recover that is going to be different. It's going to be now the convergence in the transition probability. It's a bit more difficult, but the same idea goes in the fact that when you use the convergence of a transition probability, you desire in a way that the kernels are failure, as it's called, and the continuity and the starting points is preserved. So that's the kind of convergence we use here. Essentially, we have the same story. We have exchangeable stick breaking or Markov stick breaking, whereas these are Markov or exchangeable. And the story goes again. There's a lot of theory here. Of course, I'm not writing down. This second bit is the bit that I'm doing with Antonio Lioya, Maria Fernanda, and Igor Prunzer, essentially. And this bit's already published. I'll give you the ideas. So the same story goes. The only thing is that we cannot do it in automatic as we did it for the exchangeable case. So for that, we need an extra condition, right? And the condition essentially is that in the stationarity, let me try to, okay, here it is. We need the condition satisfied for the transition densities that are continuous. So in other words, to make it sweet, we need failure transition densities. And a failure transition density means that you have continuity in the starting point. Of course, that includes many Markov processes, all Levy processes or diffusion processes or failure processes, pretty much. So essentially, you have all these kind of things, right? So that is something that continuity we need in order to achieve this result. Again, we have the same results when you move that in a Markovian setting. In a particular case, with the stationary distribution of the length variables is beta 1 theta in order to recover the Dirichlet process. We recover the Dirichlet process with this convergence indicated in a different sort of way. All the geometric process would degenerate in a particular point. And this is the convergence I was saying before, right? The initial point. Okay, so essentially that's the story. The story goes very simply because the message goes like this. You want to construct a different model, or for your applications is better a different model, you can construct it doing exchangeable random variables. To construct exchangeable random variables is very simple because it's the way we use it in Bayesian statistics all the time. So you start with a beta distribution, you have some parameter, put a prior, immediately you have exchangeable sequence, right? And you can construct it in order to have the beta that you want or the distribution that you want, right? Or you can construct the Markov processes, take any Markov processes you like in discrete time that has the marginal that you want to put as the distribution of the length variable. And then you have another model. In this case, I was showing it in a no parametric way. I was modeling again the length variables through species sampling processes, but can be done in very simplistic parametric way as well. So there are bunch of models there to be investigated where things can be calculated or not, right? So that's pretty much the message I want to pass on here. There are some nice plots. Well, this is an example that we did in the paper with Theodoro Nicolaris. Essentially, what it takes, you take a transition density that always, to take a process. This process is very famous in the literature. because it goes in the continuous setting, it's a process known as the Wright-Fisher model. In the discrete setting, it's just a stochastic process that goes like this, right? Say you have points here, and you have a band here. So I will put the lines just to make it easier to follow. But these are betas always. Well, imagine these are beta distributions. So the marginal distribution is always beta with this parameter, right? You have a dependence, but it's not IID. It's not like the dirichlet. But of course, in a limit, you obtain the dirichlet. And in the other limit, you obtain the geometric. So in that case, we have this construction here, and we studied this model. And this is just plot of the transition density when the initial point is this one here. You know that you degenerate in the stationary distribution, right? So
in general, when you consider this dependent things, do you want to keep the same marginal distribution all of them?
That is something that we don't want to do. We did it here for this example at generalization. If you want to do the two-parameter Poisson-Dirichlet process, which each has its own, then it's not longer a stationary Markov process. So the theory goes beyond a stationary Markov process. We have done it, and in some cases, like this one that I'm showing right now, it can be done. So you have the spike and slab, as we call it, spike and slab transition density, which is nothing else than the Harris processes. Essentially, this is a very nice process that I always use to teach Markov processes, because it's a process that if you take that raw in continuous time, then you have a process that goes like that, has a jump, goes like that all the time. So marginal to this process can live in any space, whatever space, is completely dependent with certain probability, completely dependent, meaning it stays in the same VI with the same probability, or jumps to a completely independent one. So it's a nice Markov process that plays with one parameter, fully dependence or fully independence. And you can do everything with that. Computer, resolvent, semi-group, everything. So it's a very nice example. So that process, if you use that process for the length variables, then you can recover again. Here we're using it with the same marginal, but if you use it as, again, with transformation that allows you to have the IID, they are independent, but not identically distributed, needed for the two parameter Poisson-Dirichlet, you can also do it. Oops. So another thing, and I probably finish with this, pretty much the most important bit. We are able to model the probability of since the weights can be the Dirichlet, they are not decreasing all the time. They are only decreasing in the limit when you have the geometry. But you can model the probability of these decreasing weights. And that is very useful, not only for statistics, but also for other things. Oh, sorry. But essentially, oops, that probability is given in the spike and slab transition, is given with this expression. For the Dirichlet process, is given for this expression, and for θ = 1 is actually given for this expression. So it's just a linear combination of that type probability. So the type probability tells you, go here, the type probability tells you the probability of the weights being in order or not. So it's going to tell you, it's going to control you how much you get confused and how much not. And there is a lot of discussion again in the literature, because sometimes you need that label switching in order to prove new values, right? So you need it. It's not that you don't need it. It's not that it's always something to hate. That label switching helps a lot in order to prove new elements in the distribution and see whether it is good or not. It's just that it has identifiability issues in the likelihood, and it does not correspond one parameter set to one point in the likelihood. You have many to the same point in the likelihood. That is what is going on here, right? So essentially, this allows you to control that. So I have to finish with an example. Otherwise, you think it's something that cannot be used for anything, right? So essentially, I take a very simple example, which essentially is a mixture of normals. I do the mixture with this model, this changeable one, right? Which essentially tells you, since this is discrete, is the mixture of normals that we sort of use in mixture models. Of course, we have an infinite number of components, and the W's here, the weights are random, right? So this is a very simple example. And then I take a normal Wishart inverse distribution as a prior for the prior guess at the shape of this distribution, this mu 0. I take the Dirichlet process, where is this? Yeah, the changeable stick breaking process with this beta distribution. And I model also the type probability. I put a prior on the type probability, a uniform. Here you can put a prior or not, depending what you want to do, right? I want to just fit this. So I want to put a prior. So what is doing this prior intrinsically is modeling whether you should, at the state of the MCMC, you have a different configuration. Shall I do a bit more of the label switching, or shall I just do more order weights? So the prior is actually playing that role here. So this is an example that Marifer likes. She likes a lot of animals and then dogs, and she created this data set, which are, I think, 7 normal distribution, which looks like a paw. Students. And then these are the data, and these are the density estimate of the original data, right? So, and these are the cluster estimation using that allocation variable for those, the Dirichlet process, the geometric process, and the changeable stick breaking process. So I leave that for interpretation. There are many things. The geometric process always overestimates the number of groups. And that was one of the problems we didn't like when we wanted to do Bayesian no parametrics through geometric processes for clustering. So that sucks pretty much, right? It was overestimating a lot the number of clusters. And whereas the Dirichlet is good, or the 2-parameter Poisson Dirichlet. So these are this exchangeable process is doing something in between. Probably it's easier to notice in this last. So this is the true one. This is the density estimation. This is the geometric process. You see, it has a lot of bumps here. This is the one based on the clustering. Sorry, the density estimation for the clustering. And this is the Dirichlet process, and this is exchangeable. So clearly, the exchangeable is the one that is making good job here, I would say, in this application. It's just an example, right? But of course, there are many ways to compare that. So I think with this, I finish. There is a paper, the one with the beta binomial, that was the one that came out first in Electronic Journal of Statistics, and just a paper that is to appear in with the exchangeable stick breaking priors, and the Markov we are pretty much done with it. Hopefully to submit soon. And shout any questions, please.
Ramses, was a wonderful talk. Unfortunately, we're running a little short of time. There is a class right after, so maybe there is time for 1 or 2 questions. A couple of quick ones.
So if you don't have extendability or dependence, is it easier to achieve full support or harder?
If I don't have exchangeability?
Or dependence?
You mean the full support? I don't think it's difficult at all in any of the cases. It's very simple to, there is a paper by Viciri, I don't remember, Ongaro and Viciri, where they prove it very simply. I mean, the conditions are very, very simple. No, it's not difficult. To achieve full support is not difficult. Not difficult at all. Summing up to 1 is different.
Yeah, quick question about the earlier questions. So the identifying the ways, I never understand. So any permutation give you exact same density.
Yeah.
How that affects the density estimation? Because at the end of the day, your probably prior mass on a particular density will be just the total mass of the equivalent class, right?
You mean the posterior, right?
Yeah.
How up affects the posterior?
Yeah,
a lot, because essentially you are not identifying the value that the predictive a lo mejor español. Sorry, the predictive perhaps would be better, right? In that sense, to remove that, but it's not always easy to compute.
Yeah, but yeah, so the weights is hard to identify because
that's right.
But then all just equivalent weights imply exactly the same density.
Yeah, that's right.
Then how the posterior probability of that density becomes harder to estimate than under the geometric process.
I mean, it's easier in the geometric because essentially you are imposing at the beginning an order sort of weight. I mean, it's not solved. In that is the point that I was saying, that is not solved at all, because it's not solved at all. But since you are imposing this ordering, it goes a lot simpler when you do the posterior, because you are not at the beginning, you are not sort of like saying, look, it's completely random, right? So, and then how it goes in an MCMC is that you are jumping between one place and another. And that actually kills many MCMC methods. That's the posterior, because we're doing posterior inference with true MCMC. Probably to some different way, like doing posterior means or whatever, a different story would be. I mean, like, yes.
Comment of scalability.
Sorry?
On scalability.
Scalability. Wow, she killed me with that one. This morning I spoke with so many people, and all of them are doing scalable things. So essentially, scalability is tough. It's a tough job. Sinead, I think, might be able to reply to these questions because she's doing that with these models. And I think what she's doing can be done also with these priors. She's doing like this bagel tricks. I don't know. Yeah, it's an issue. Sorry.
Okay, I think we have to wrap up now. If you have any